Yesterday we introduced the concept of magnetism. We defined a term called magnetic domains. Who remembers from yesterday what a magnetic domain is? Tiny little region inside a ferromagnetic material that's represented by arrows. What's a ferromagnetic material? We can't really understand what that means unless we understand what every word in that definition means. What's a ferromagnetic material? Yep. Yeah, it's something that can become magnetized, something that has the ability to become magnetized. Give me an example of a ferromagnetic material. Iron, steel, lots of other things as well. Anything that contains iron and some other things as well. Give me an example of something that's not ferromagnetic, something that's pretty obvious that's not a ferromagnetic material. Milk. Good. Milk is not a ferromagnetic material. I don't know, though, actually. If you look at the ingredients, there might actually be iron in milk. I'm not really sure about that. So it's not particularly ferromagnetic anyways, that's for sure. Obviously, glass, plastic, whatever. Just because it's a metal, though, understand this. Just because it's a metal doesn't mean it's ferromagnetic. Copper, for instance, is not ferromagnetic. Okay? Steel is, copper isn't ferromagnetic. So it's not, generally say metals are good conductors of electricity. It doesn't necessarily correspond to ferromagnetism. Just because it's a good conductor doesn't mean it's a ferromagnetic material. It has to do with, that's a good question, what prevents it from being ferromagnetic? Same thing that prevents anything else from being ferromagnetic, like a piece of paper or plastic or milk or whatever the case may be. In the end, it doesn't have domains. Now, what's this whole thing about domains? A domain, we say, is a tiny little region inside this material that we represent by arrows. Of course, it's not really an arrow that's inside it. It has to do with patterns of electron spins inside this this material. We don't get those same patterns formed in milk that we get in steel. We don't get the same patterns formed in copper as we do in steel. Now, why not? I can't really answer that question, but we don't. If I've got a ferromagnetic material with a whole bunch of domains pointing in random directions, there's a couple ways that I can align those domains. So there's a couple ways that I can turn this into at least a temporary magnet. What's one of those ways? What's the easiest way? What's the simplest and the most obvious way that I can align these domains, point them all in the same direction? Patrick? Yeah, bring another magnet nearby. The closer you bring it, the more of an effect it's going to have. The longer you keep it there, the more of an effect it's going to have. The stronger it is, the more of an effect it's going to have. But anytime you bring this magnetic field nearby it, you're going to align these domains. It's been found, buildings have been built with steel for 100 years. It's been found that buildings constructed out of steel decades ago have become magnetized over the years. The concrete can't become magnetized because it's not ferromagnetic, but the steel frame of the building is ferromagnetic. What magnetic field is it exposed to? The Earth's magnetic field. So there's a distinct polarity associated with steel-framed buildings that have been around for decades. Now, it's not an overly strong effect because the Earth's magnetic field, as you saw yesterday, is very weak, about 10 to the minus 5 Tesla. But it's there, and it's measurable, even in these buildings, independent of the Earth below it. Even in these buildings, there's a distinct magnetic polarity associated with it. Okay? Anytime you bring this magnet nearby, including the Earth's magnetic field, you're going to, at some level, align the domains at least to some point. Now, what's the other way that we can align these domains in this blue ferromagnetic non-magnetized material? Rob? Yeah, wrap a wire around it. Now, it's not good enough just to put the wire around it. If you put the wire around it, all you have is a wire around a piece of steel. What do you do with the wire? Yeah, attached to a battery so that you've got a current going through it. That's going to create a magnetic field, as you're going to learn a little bit more about today. And that magnetic field that's caused by the current in the wire is going to magnetize the ferromagnetic material inside it. Okay? It's going to cause the domains inside to become aligned, at least partially, in one direction or another. One more quick question with this one. what do we do? What happens if we've got something that's become ferromagnetic? It's been magnetized with a distinct polarity, south pole and north pole. By the way, the domains always point from south to north. Okay. Magnetic field, remember, we'll talk about that one in a second, but the domains always point from south to north. What happens if we cut that magnet in half? We take a hacksaw and physically chop that magnet in half. Obviously, we're going to have two magnets now, right? One magnet that's south and one magnet that's north. Or tenor? They're both going to be north and south. Domains point from south to north. If we have domains pointing in a particular direction, and we do, even when we cut this in half, then we're going to have a south and we're going to have a north. Domains don't point from south to nothing. They point from south to north. If they point somewhere, there's got to be a north. If they point from somewhere, there's got to be a north. So we're going to have south and north in both magnets there. We define the direction not of the domains, but of the magnetic field in two ways. Who can remember one of those definitions? I'll give you a hint here. The direction of the electric field, remember in our last unit, was defined as the way that a positive particle would move if placed in the field. Magnetic field is a similar definition, but it's not a positive particle that we're going to put there. Something even simpler. Rob, what's it going to be? That's what happens when you start scratching your shoulder or something. I think you're putting your hand up, and then I call on you. Sure you do. You're going to put something in this magnetic field and see which way it goes. That's the direction of the magnetic field. What is it that you put there? What did you put in the magnetic field yesterday when you were trying to determine the direction of the magnetic field? What did you physically do yesterday? A compass. It's the direction that a compass needle points when placed in the field. Okay, the north end of a compass needle is the red tip that you're always looking at. The direction that the north end of a compass points when placed in the field is the direction of the magnetic field. Now, the north end of a compass is going to point which way? North or south? North is going to be attracted to the south, right? So in the end, the magnetic field is also going to be from north to south, just like an electric field is from positive to negative. So the way that a compass needle points when placed in the field, and it's going to be from north to south. We drew some magnetic field diagrams yesterday. Okay, I'm going to bring up a couple of diagrams here. Shapes are all there. I'm just going to simply ask you to tell me the polarity of these. What's the polarity of this? First one is going to be what? North or south? How do you know it's south? Because the magnetic fields point towards it. This one has got to be north because you can't have a single magnet with a single pole. You can't have both ends south. One end's got to be south and one end's got to be north. So if the first end is south, second end has got to be north. But you also know that it's north because the magnetic fields go away from that right side, the north end. What do we got here? First of all, let's just take a look at these two poles right here. I want you to tell me if these are like poles or opposite poles, first of all. Don't tell me whether they're north or south or whatever. Like poles or opposite poles? Opposite poles? How do you know that? Because the field lines go from one to the other. All right, so they're opposite poles. One's going to be north, one's going to be south. Which one's north and which one's south? First one, north or south? South. Second one is north, because the field lines go away from north and toward the south. Well, this is south, then this has got to be north, because you've got to have a magnet with two poles. But you also know that the field lines go away from this north and toward the south. This one's going to be a south pole. Again, field lines go away from north and toward the south, and you've got to have two different poles in that second magnet. Finally, the diagram that we have up on the board here now, these two in the middle, like poles or opposite poles? Like poles, because you can see these field lines repelling each other. They're going to be norths or both souths. They're both going to be norths. We know that because the field lines go away from north. Sorry, said they're both north. Wrote down the wrong thing. The field lines go away from north and go towards south. Where's the south? Where do they go? The south is over here. Ultimately, if we drew enough of these field lines, they would go around like this, pointing towards the south. And these guys would go around like this, towards the south. Does that make sense? I can tell you right now, with 100% certainty, then on your next unit test, you will see field line diagrams. Okay, whether they be electric field lines or magnetic field lines or both, you will see at least one question where you have to be able to determine what the fields look like surrounding either charges or surrounding poles, magnets. You will probably have to do that on your diploma exam as well. I'd be about 98% sure that you get a question on either electric fields or magnetic field diagrams on your diploma exam. But I'm 100% sure you'll see it on your next unit test. Those are gimme questions. Okay, we've got to get those ones right. We're going to see some hard questions. These aren't hard. Okay, if you're having trouble with it right now, then make sure you see me and get a hand with it. We also talked about the Earth's magnetic field yesterday. The Earth's magnetic field is the direction that a compass points when placed in the field. It's going to be this way, towards what we think of as the North Pole, right? Northern Canada, okay, the Arctic Ocean. It's going to point away from Antarctica. Well, if the definition of direction of magnetic field was correct, the way that a compass points when placed in the field and toward the south and away from the north, then that means that up here is going to be the South Pole and down here is going to be the North Pole. Geographically, that's not correct. Geographically, north is Canada, south is Antarctica. But magnetically, south is Canada and Antarctica is north. Does that make sense? All right. Let's go on a little treasure hunt here. Let's go back to the year 1819. A guy named Hans Christian Oersted is taking a look at a compass. I don't know, maybe he's looking for a treasure. Okay, he's got a little treasure map there. X marks the spot. I don't know. He's got a compass. He's looking at this compass and he finds that it points in which direction? Magnetic south, right? It points in the direction of the magnetic field, which is towards magnetic south. But all of a sudden he flips on a switch or something and he gets an electric current going through a wire. All of a sudden the compass that's nearby this wire gets deflected. The compass needle no longer points towards magnetic south. Maybe it points toward the east or toward the west. He flips off the current a little bit later and realizes, wait a second, the compass went back to the way that it was before. Flips it on, compass needle gets deflected in a different direction. Flips it off, on, off. And he notices that every time he does that, the compass needle gets deflected in a direction other than the way it's supposed to, other than magnetic south. The only thing that will deflect the compass needle is a magnetic field. So the only logical conclusion from that is that the electric current must be generating a magnetic field. Almost 200 years ago, arguably the single most important discovery for technology was made. And that is that an electric current or moving charged particles generate magnetic fields. That's huge. We'll talk a lot more about this unit. Why that's so important, where that applies in technology that we use today. It's in almost everything we do today. The idea that moving charges generate magnetic fields. 6 years from now, it'll be 200 years since that most important discovery, almost most important discovery ever in terms of technology was made. Now yesterday and earlier today in a review, we looked at the shapes of magnetic fields surrounding bar magnets and surrounding combinations of bar magnets. What's the shape of the magnetic field surrounding a moving charge that generates a magnetic field, surrounding a wire with a current in it that generates a magnetic field? Well, it's actually quite simple. Before I talk about that, though, I want to define some notation for direction. Clearly, if I draw an arrow to the left, then that means something is pointing to the left. If I draw an arrow to the right, that means something is pointing to the right, up or down. That stuff's easy. But what if I want to show something moving away from us or towards us, into the page, coming out of the page towards you guys? I'm going to use two new symbols, an X and a dot. The X is going to mean going into the page. So if this pen is the electron or the charged particle, it's going this way. It's going into the page. If this pen is the electron, this time it's going this way. It's going out of the page towards you guys. From your frame of reference, okay, if you do an X on the page, on your page that was horizontal on your desk, then whatever it was, the electron, the proton, whatever it is, would be going down like this into the page. X means into the page, dot means out of the page. How do you remember that? Arrows are easy to remember, right? Dots and X's, easy to get those mixed up. I'll tell you how I still, to this day, remember the difference between the dot and the X and which way's which. And I was 4 years old. I had a neighbor across the street that was 5 or 6. He was a year or two older than I was. We used to play together sometimes. Sometimes we'd go down to his basement. In his basement was a pool table. We'd play pool, try to play pool lots. Beside the pool table one day on a stand was a dartboard. And I remember very clearly the two of us playing darts on this dartboard, unsupervised. I was 4, he was 5 or 6. We weren't very good. So you throw a dart at the dartboard, sometimes you missed. When you did hit the dartboard, the dart would just kind of hit the side and bounce right off. So that's what happens to me. I remember throwing these darts at it, I miss, or I hit the dartboard, but the darts fell off, whatever. I remember walking over, picking up a dart that was beside the dartboard, bending over to pick it up, standing up, and I remember all of a sudden, I got this dart in the back that stuck in my back. Okay, he picks the time when I'm standing there to actually throw a dart that will stick into something, as opposed to when he's actually throwing it at the dartboard. I couldn't see it coming towards me because I was facing the other way, but I couldn't see it coming towards me, but I can see it coming towards me, if you know what I mean. I can visualize this dart in slow motion coming towards me, coming towards my back, and then thud, sticking in my back. When I see this dart coming towards me, at least in my mind, I see this sharp thing with a point coming towards me. Okay, if you see a dart coming towards you, it's going to look like a dot. If I visualize that dart going away from me, then what's it going to look like? It's going to look like an X. The fins of the dart are going to form an X. So as the dart is coming towards me, or out of the page, towards me and you guys, it's a dot. As the dart or the electron or whatever it is going away from us, we're going to see an X. Make sense? All right, so what does the magnetic field look like when you've got, say, an electron that's moving into the page, as represented by this X? The magnetic field will always be circular. There's one magnetic field line. There's another magnetic field line. There's another one. There's another magnetic field line. What do you notice about the spacing of these magnetic field lines? The shape is all the same, right? They're all circles. They're what we call concentric circles, circles around one another. Different field lines get bigger and bigger and bigger. What do you notice about the spacing of them? Yes, the spacing between them gets greater and greater and greater. What does it tell you about the strength of the magnetic field the further you get away from the charged particle that's causing this magnetic field? Yeah? Curtis? What does it tell you about the strength? I thought your hand was going up there. What does it tell you about the strength, the fact that these field lines are getting further apart from each other? No? I think it's weaker, right? And that only stands to reason, right? If it's this charged particle that's moving, that's causing this magnetic field, the further you get away from what's causing it, the weaker the magnetic field is going to be. The further apart the field lines get. What about the direction now? Magnetic fields are vector fields. They have to have a direction. You go from north to south, but we don't have, it doesn't appear to have any north poles and south poles here. So what's it going to look like? We're going to use a rule called the wire grasp rule to determine the direction of the magnetic field. The wire grasp rule has two parts to it. You're going to take your hand, your left hand if it's a negative particle, your right hand if it's a positive particle. If we're talking about electrons here, we're going to use our left hand. And we're going to use two parts of our left hand to determine which direction the magnetic field is pointing. My thumb is going to point in the direction of the moving charge. Or if that moving charge is moving through a wire, then we would say in the direction of the current. So in this case, I'm going to take my left thumb, because it's a negative particle, and I'm going to stick it into the page. For me, into the page means toward the front of the room. For you, if you have it drawn as an X on your page, it's going to be down towards the floor. You're going to stick your thumb in the direction of the current, or in the direction of that charge, which is into the page. Your fingers, you're going to bend your fingers. And your bent fingers are going to point in the direction of the magnetic field. You guys remember that symbol yesterday, B for magnetic field? Your fingertips, look at your fingernails. Which way are your fingernails pointing? Okay, whatever way they're pointing is the direction of the magnetic field. Now, let's try this. Stick our thumb in the direction of the current, which is into the page. Let's bend our fingers a little bit. How much do I bend them? Like this or like this? It doesn't matter. Okay, let's bend my fingers a little bit. Which way are my fingertips pointing right now? To the left, right? Which way are my fingertips pointing right now? To the right. So which way is the magnetic field? Left or right? It's both. It's left right here. It's right down here. The magnetic field is up right here because my fingertips are pointing up. The magnetic field is down right here because my fingertips are pointing down. Which way is the magnetic field? It's counterclockwise. It's counterclockwise around this circle. How would this change if it was an alpha particle, a positive particle, or some other positive particle like a proton that was going into the page? Use the right-hand rule, the right-hand wire grasp rule. My right thumb would go into the page. My right fingers would go in the direction of the field, which is to the right, above the particle, to the left, below the particle. Complete that circle would end up going clockwise. How does this work? If you've got a negative particle represented by the X. What's the X mean again? Sorry, a dot, I mean. The X is the one we just did, the dot. What's the dot mean? Out of the page. Something, in this case an electron, is moving out of the page. It's a negative particle, so I'm going to use my left hand. The left hand wire grasp rule. Left thumb out of the page. So for me, it's going to look like this because my page is vertical. For you, it's going to look like this because your page is horizontal. When my fingers are, let's draw the field lines here. When my fingers are above the wire, which is where they are right now, you look at this and you say, well, his fingers are everywhere. His fingers are like here and here and here. Like, what are we looking at exactly? We're looking at the fingertips. Just the fingertips. Right now, my fingertips are right above the wire, and they're pointing to the right. Right now, my fingertips are to the right of the wire, and they're pointing which way? Down. And so on. So that the field in this case is clockwise. Left hand for negative, right hand for positive. Thumb in the direction of the particle or the current. Fingers bent a little bit, fingertips pointing in the direction of the magnetic field caused by that particle. Let's try this one. Let's say we've got an electron or electrons in a wire, doesn't matter, moving towards the left side of the page. We want to know the direction of the magnetic field up here above the wire, down here below the wire. We want to know the direction of the magnetic field behind the wire. and we want to know the direction of the magnetic field in front of the wire. It can be useful when doing a question like this, where the charged particle isn't coming away from you or towards you, to visualize this with some kind of manipulative, like a pen or a ruler or a Slurpee straw, Rob, or whatever the case may be. Make that your wire. Okay? Let's say this pen right up here, this board marker here, is my wire with the current going towards the left. Okay? Let's stick my thumb, my left thumb, because it's an electron, towards the left. Let's bend my fingers. I want my fingertips to be directly above that wire. So let's do that. Let's put my fingertips directly above the wire. When my fingertips are right above the wire, which way are they pointing? Out of the page. If my page is vertical, they're pointing towards you guys. If you do it on your page, then it's going to look something like this. Fingertips are above the wire. They're still pointing out of the page. When my fingertips are below the wire, which way are they pointing? Well, here's the wire. Okay, let's turn it around so my fingertips are directly below the wire. This is the plane of the page, right? Which way are the fingertips pointing? Into the page. Right? If I'm the plane of the page, then my fingertips are pointing into the page. What about behind the wire? Right now, from your frame of reference, my fingers are behind the wire. Which way are they pointing? Which way are my fingertips pointing? If I had needles on the end of my finger, where would you not want to stand? Where would you not want to put your hand? Above it, because they're pointing upwards. They're pointing behind the wire. They're pointing upwards. And in front of the wire, they're pointing downwards. Now, let's be really, really careful here. For me, because my page is vertical, my fingers are pointing upwards and my fingers are pointing downwards, right? For you, it's not up and down, right? It's toward the front of the room and towards the back of the room. So let's change that notation ever so slightly. Behind the wire, instead of saying up, let's say it's toward the top of the page. Instead of saying down, let's say it's toward the bottom of the page. If our page, our piece of paper is our frame of reference, then let's express our answers in terms of the page. Now, how do we reconcile that with these diagrams that we drew back here for the negative particle going into and out of the page? Here we had circular magnetic fields. Here we do as well. If this is your wire, the magnetic field going out of the page above the wire into the page below, the magnetic field ends up looking like this. It's still circular, but it's going out of the page here, it's going into the page here, it's going up the page here, and it's going down the page right there. Right? What I'd like you to do right now, and there's not enough of these to go around, so you have to share a little bit for the time being, is take a look at worksheet number 10. Worksheet number 10, I believe, has 6 questions on it, and it's going to ask you to find the direction of magnetic fields, and the last couple questions, it's going to kind of reverse it all and ask you to find the direction of the moving charge. Let's see what you can do with that for the next few minutes, and then we'll take a look at it as a group. Do all of these questions as a group once you've had a chance to finish this up. Let's take a look at worksheet number 10 now. First one says, draw the magnetic field surrounding the wire showing electron current below. It's represented by an X. We've already done this, right? This is one of the examples that we did, but let's go through it again. If it's represented by an X, that means the electron is going which way? Into the page, out of the page? It's into the page, right? If we picture that dart going away from us, it's going to look like an X. So this electron is going into the page. We know the shape of it is going to be circular, concentric circles. We know the direction of it is going to be found by the left-hand wire grasp rule. Left hand because it's a negative particle. Wire grasp rule, we're trying to find the direction of the field here. Thumb, left thumb into the page, fingers are going to point which way? To the left, above the wire. To the right, below the wire. The net effect of that is going to be counterclockwise. So the magnetic field is going to be counterclockwise in that one. Number 2, we're representing electron current here by this dot. That means it's coming out of the page. The magnetic field is circular. The direction of the magnetic field is going to be found by the wire grasp rule. Left thumb out of the page. Fingers are going to go, doesn't matter where I put my fingers, it's going to end up being clockwise. So the magnetic field caused by that wire or caused by that moving charge is going to be clockwise in this case. 3, this is one of those tougher ones, 3 and 4. 3, we want to find the direction of the magnetic field surrounding this electron current moving to the right. This is one where it might be helpful to have that little manipulative, to take the pen, to take the piece of paper all rolled up, to take the ruler or whatever it is, and make it your wire. We have our wire pointing towards the right side of the page. My left thumb is going to go towards the right. My fingers right now are above the wire. Which way are my fingertips pointing? If I've got those needles on the end of my fingers, what's going to get hurt? My face, right? My face is the plane of the page. So the magnetic field is going into the page at that point. Above the wire, it's going into the page. Below the wire, it's going out of the page. My fingertips right below the wire going out of the page. My fingertips now are in front of the wire. Which way are they pointing? No, don't say up. Towards the top of the page. Okay, my fingertips are pointing towards the top of the page. Now, with the way my page is oriented, which is vertical here, then toward the top of the page is up. But for you, toward the top of the page isn't up. So we're going to say it's toward the top of the page. And behind that wire, we're going to say the magnetic field points down toward the bottom of the page. Don't say down, but toward the bottom of the page. Number 4 gives me an alpha particle that's going up toward the top of the page. This time it's going to be the right-hand wire grasp rule. Thumb in the direction of the particle, right thumb in the direction of the particle, fingers in the direction of the field, bent a little bit. Right now my fingers are in front of the wire. Which way are they pointing? Here's the plane of the page. My fingers are in front of the wire towards the right. Behind the wire, my fingertips point towards the left. To the left of the wire, my fingertips point out of the page. Don't say toward the back of the room because it depends on how your page is oriented, right? If this is the plane of the page, then my fingertips are pointing out of the page. Here, my fingertips to the right of the wire, my fingertips are pointing into the page. Okay? That's the frame of reference we want to use here, relative to the page. 5 and 6 are a little bit different still. 5 gives you a magnetic field surrounding a moving electron. That magnetic field is going to be clockwise. This is like algebra. This is like rearranging equations. If I gave you an equation or a question in Physics 20 said, here's the speed, here's the displacement, what's the time? You would take v equals d over t and rearrange it to solve for t, which is not the normal thing you solve for. Usually you solve for v. Here we're going to take a wire grasp rule. We're going to rearrange it. Instead of solving for whichever way my fingers point, I'm going to solve for whichever way my thumb's going to point. So my fingers here, I know that. I know that they're going to point clockwise. My thumb points whichever way it points. If I make my fingers point clockwise, my thumb is going to point out of the page. In question number 6, I think it says it's a positive particle. Yeah. In order to make my right hand fingers point clockwise, my right thumb must be into the page. Is that clear? I told you on your unit test, and most likely on your diploma exam, you will see those magnetic field diagrams. You will. I'm not taking that back. You will also see the wire grasp rule used on your unit test, and almost certainly on your diploma exam as well. So far today, we've looked at two concepts. Part of it was yesterday, right? Part of it was yesterday, but we reviewed it today. Two concepts where you will almost certainly see questions on your diploma exam on. Okay? That's 1/25th right there. That's 1/25th. It doesn't sound like a lot, but 1/25th of your diploma exam, those two concepts right there. Okay? 4% of your diploma exam right there. All right, if you guys are good with that, then I want to just go through one more hand rule for you. This one we're going to call the Coil Rule. Unfortunately, your textbook, if you ever refer to that, also calls this one the wire grasp rule. I think that's stupid because you've got two different rules named the same thing. I renamed it because I think it's silly to call it the same thing. The wire grasp rule we're going to call the rule that finds the magnetic field caused by simply a moving particle or a straight wire. You want to find the magnetic field caused by this solenoid, this coil of wire. That's all a solenoid is, right? It's a coil of wire wrapped around something. You want to find the magnetic field caused by that? We're going to use the coil rule. Now, if you remember the wire grasp rule, the wire grasp rule said your thumb points in the direction of the moving charge. And your fingers, your bent fingers, point in the direction of the magnetic field. For the coil rule, we're going to say our thumb points in the direction of the magnetic field, and our fingers, our slightly bent fingers, are going to point in the direction of the moving charge, or in other words, the electric current. So it's the exact opposite rule. Now, the point of this is to usually find the polarity of this. If we've got a piece of steel or a piece of iron inside a coil of wire, inside a solenoid, then you will make an electromagnet out of that piece of steel or out of that piece of iron. You will magnetize it. It will pick up thumbtacks. It will pick up, in a junkyard, it'll pick up cars. And that's how they move cars back and forth in a junkyard sometimes is got a giant electromagnet with a whole bunch of steel and then a whole bunch of wire wrapped around it. You flip on a switch, all of a sudden it becomes magnetized, it picks up the car. You move it over there, you turn off the switch, it becomes demagnetized, it drops the car. You got this piece of steel or whatever ferromagnetic core inside this coil or inside this solenoid. We want to find out which is the north end, which is the south end of this new electromagnet. Here's how we do it. I want everybody right now, take a piece of scrap paper. Grab a piece of scrap paper at the back if you don't want to rip one out of your binder. Back white rack there. And I want you to roll it up like this. You're going to make a coil of wire out of this piece of scrap paper. It's not hard. This is like kindergarten arts and craft, right? Except in kindergarten you make little crafts of the Easter Bunny. In Physics 30 you make little crafts of solenoids. Otherwise it's just like kindergarten, right? Take this solenoid that you just made, this wrapped up piece of paper, this coiled up piece of paper that you just made, pretend it's your solenoid. Now, you can see I'm going to draw one up here for you. You can see in this example that the electric current is going to leave the negative end of the battery and it's going to go counterclockwise around here. The way that I have this drawn, the current is going to go up the wire in behind the core and down the wire in the front. Up in the back, down in the front. Up in the back, down in the front, and so on. What I want you to do now, remember you're taking your fingers in the direction of the moving charge. In front of this coil, my fingers are going to point down. Okay, this is the front. Fingers are going to point down. Behind the coil, my fingers should point up. Doesn't matter where you put your fingers. Just make sure that it's either up in the back or down in the front. Okay, you got it wrong there. Okay, because your fingers are going down in the back. They should go up in the back or down in the front. Okay, now you get them going up in the front. There you go, there you go. Now it's going up in the back. Yep, that's fine. So it doesn't matter. Guys, look at me up here, okay? As I put my hand like this, that doesn't work. Because if I wrap my fingers around here, they're going down in the back, up in the front. That's not what I want. Okay, I want them going, you got to turn your body a little bit, that's okay. Turn your body a little bit. I want it so that my fingers are going up in the back or down in the front. Everybody do this so I can see if you're doing it right there, okay? Yes, it would. But we're talking about electrons, so you're going to use your left hand. Yeah. Okay, so don't hold your paper like this, guys. Hold your paper horizontally. I want to see your fingers up in the front or down in the back. Sorry, up in the back or down in the front. Yours are backwards. Yours are backwards there. Sergio. Yeah, wrong-handed. Okay, that's good. Yeah, up in the back. No, the part that you're looking at is the front. You look at the front of the page, right? Yeah, that's right. All right, so everybody's got their fingers correct here, I think, now. We're talking about down in the front or up in the back. Which way is your thumb pointing? Each and every one of you, which way is your thumb pointing? Towards the left. So the magnetic field inside this coil, inside, is going to be pointing to the left. Now, the magnetic field inside this coil is like domains inside a magnet. Domains inside a magnet point from south to north. So the polarity of this new electromagnet, this solenoid that was just made, is such that it's north on the left side and south on the right side. Remember, your thumb is pointing in the direction of the magnetic field, but it's the magnetic field inside the coil. So the magnetic field inside the coil is pointing to the left. The left side is therefore got to be north. Is that good? We learned that the magnetic field goes from north to south, right? But that's outside of a magnet. Every once in a while, we have to analyze the inside. Then we treat it like domains. It's going to point the opposite way to the magnetic field outside, which is going to be from south to north. Okay, let's try another one. Keep your coils. Don't throw those away yet. Let's say we've got our iron core or a steel core here. Let's say we've got our battery oriented like this time. The negative end of the battery, the negative end, by the way, is always the short end of the battery. And the electric current always goes away from the negative side of the battery towards the positive side. So it goes like this. It's going to go up in the front, and then it's going to go down in the back. Up in the front, down in the back. Up in the front, down in the back, and so on. You need to take your fingers now, take your coil, take your fingers, and make sure that your left hand fingers are pointing up in the front. Or down in the back. Doesn't matter, backwards. Okay, good. I get a kick out of this. I do get a kick out of this sometimes. It's fun to watch. Wait till we do another hand rule called the hand rule for deflection. We'll do that tomorrow. Wait till we do that one. It's entertaining for me sometimes as a teacher to stand up here and watch you guys like twist your hand around in all kind of crazy positions trying to do something that really you could have done if all you had done is turned your body like this or something like that. It's especially fun during exams to watch people doing that. Remember, fingers got to go up in the front. Okay, up in the front or down in the back. It doesn't matter which one. Okay, wrong. Okay, your fingers are going down in the front there. Yeah, good. Yeah, your fingertips. No. That's the back.
Because that's the back of the...
Because you're looking at the front, right? You're looking at the front of it. Okay. As long as you understand what your frame of reference is, I suppose it doesn't really matter. So my fingers are going up in the front. Which way is my thumb pointing? Towards the right. If my thumb points towards the right, then that means the magnetic field inside is toward the right. That means that this end is going to be south and this end is going to be north. Let me try one more, okay? One more example here. This time, isn't this the same? This is the negative end of the battery. This is the positive end. The electrons are going to move this way, right? They're going to move clockwise, same as they did in the last one. Notice how I've got the wire set up this time, though. The wire's kind of flipped around. This time the current is going up in the back, down in the front. Up in the back, down in the front. So you can't just memorize, oh, look, the current's going down in the front, or the electrons are going clockwise or counterclockwise. This is my answer. You can't do that. Because just because the current is going clockwise in this problem, just like it was in the last question, doesn't mean that the magnetic field is going to be the same. I've got my wire set up a little bit differently this time. The current is down in the front. Make sure your fingers go down in the front or up in the back. Down in the front or up in the back. There you go. Got it? Tanner, you got it? You're looking at the front of that coil right now, right? Don't worry about your thumb right now. Don't worry about your thumb right now. Worry about your fingers. Okay, your fingers are in front of the coil and they're pointing down, right? Now, which way is your thumb pointing? Towards the left. So the magnetic field inside this coil is pointing towards the left. That makes this end north and this end south. See how I got, even when the current was going clockwise, as it was in the last question, see how I got a magnetic field that was reversed? Just because of the way that I had the wire set up around it. Okay? Does it kind of make sense? Here's what I want you to do now, please, for homework. And you got almost 15 minutes to work on this, too. I want you to do some check and reflect questions on page 592. No, not all of them, but most of them. The questions that I'd like you to work on 592 are number 1 to 2, 5 to 8, and 10 to 16. 1 to 2, 5 to 8, and 10 to 16. Get those finished in class, or at least get a good start on them in class so you don't have very much to work on for homework. Make sure as you're working on them over the next 15 minutes, especially with these hand rules, when you have to do one of the hand rule questions, call me over. Okay, get some help if you're struggling with it. We will review this several times tomorrow, several times the next day, several times the next day, and so on. This is important, and it's a little bit confusing. Once you get the hang of it, it's easy, but it does take us a little while to get the hang of it. Today, I don't expect you to be an expert. Today, I want you to kind of understand it. Tomorrow, hopefully you understand it a little bit more, and the next day, hopefully you understand it a little bit more still. So call me over. When I'm walking around here, call me over if you're struggling with any of these questions, all right?